So today, we're going to just talk very briefly about the different types of forces there are. Up until this point, I've kept it pretty general. I've only said things like we apply a force, push or pull, things like that. And indeed, there are a lot of different types of things that can cause forces. Right? You could attach a rocket boost or a jetpack to someone, and that can apply a force. You can push something that applies a force. You could pull something that applies a force. But then there are also some other types of forces that have to do either with gravitational fields, structure, or even surface. And so we're going to look at kind of these four main forces that we're going to focus on specifically in this chapter. Those forces are weight, normal or support force, tension force, and then frictional forces. And there are two types of those. So let's look at the first one. We have weight. So we throw around this word pretty easily, but in physics, weight is actually a measurement of force. Mass is a measurement of the quantity of matter something contains, but weight has to do with how much a planet or a sufficiently big mass is pulling on something. So there are anything that has mass, right, applies a gravitational force. So, for example, we have the obvious example. We have, the Earth with, has its planets, whatever, right? And if you're standing on here, right, the Earth pulls down on you towards it, right, because the Earth has a lot of mass. But you yourself, sitting at home, watching this on your computer, right? You have just as much force being applied. Sorry, I should rephrase that. You do have a force being applied on you by your computer, by your desk, by your chair. But that force is very, 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 very tiny because the mass of your computer, mass of your chair, table, all of those combined, even like the mass of your house, it's not very big compared to the mass of the Earth. And we're going to talk more about how those forces are actually calculated and where they come from. But for now, all you need to know is simply this, that the force due to gravity, known as weight, is equal to your mass times the gravity of the planet that you are on. On Earth, it's usually 9.81 meters per second squared, but we're just going to round it up to 10 meters per second squared. Your mass is always going to be measured in kilograms. This force, since it is a force, it is measured in newtons. And you should know that, of course, gravity is measured in meters per second squared. So we have weight. Right now, we have normal force. So normal force. Normal force, or the word normal, is actually just a mathematical term. It really just means perpendicular to. And so a lot of students, they like the word support force more than normal force, but I'm probably going to be using normal force because I'm just familiar with that. Normal force is actually one of those things where you don't necessarily need to calculate much. It just depends on your situation. So the normal force, for example, let's do an example first before, or actually let's define it. So we have normal force, and this is just going to be the force that is due to something supporting you. To support. Right, and really quickly, if we look at a simple example, let's say there's a person and they are just standing on the ground, and they're happy, right? So, right, what we're going to do is we're actually going to look at the ground right underneath where they are standing. So let's pretend we could zoom into this really, really, really closely, right? If we could see the actual atoms being interacted, right, this ground that looks pretty flat would actually bend down, right, around this person's foot, right? So pretend this is the new surface right here, and I'm going to make this a little bit more aligned, right? So, right, there are all these different atoms here, and they're bonded together, right? And they don't want to just break because they're standing, so they'll bend a little bit, right? They'll bend a little bit because your foot is on the ground, and so that's like the support force. So it kind of feels like a very compression or tension force. So that's where it comes from. But all you really need to know is this: the way you calculate it, right? So force due to support. Well, if the weight of the Earth, the weight that you have due to the force that the Earth is pulling on you, right? Let's say you have a weight of, I don't know, 1,000 kilograms or 1,000 newtons, right? Well, if the ground is supporting you with 1,000 newtons, right, you're pulling down on it. The Earth is pulling you down. You're applying a force of 2,000 newtons downwards. If the ground is supporting you and the ground is not giving way or not moving, well, that means in this case, right, as much as this one was equal to weight, right, well, it's also equal to the normal force. But the situation can change, right? Let's say all of a sudden you have someone sitting here, right, or standing here. So they're here, standing sideways. They're kind of like leaning forward just a little bit. Now maybe they are about to fall. Right, this time the normal force, right, doesn't counteract this 1,000 newtons of this guy any longer completely. So in this first example, if we were to draw a free body diagram, we'd have the weight going this way, which is Fg, and the normal force going up with the exact same amount. Notice that the normal force is perpendicular to the ground. In this case, if we draw a free body diagram, well, if this person's on an incline, weight always points down. But now, if he is on an incline, normal force points perpendicular to the surface. Right, so it's still supporting him, but it can apply a force in a different direction than being perpendicular to the surface. So that's kind of the special thing of normal force. And so if we wanted to calculate this, we'd actually have to find this angle of incline, and we'll do that much later. But just know for now, if you are on a flat surface, your normal force will, in fact, equal your weight. So that's very helpful to know. Now we have tension force. So tension is also another one we don't really have to do much calculation for. The tension is just a pulling force, a stretchy force. And kind of similarly to normal force, let's say that there is a weight and it's hanging on a ball, right? Let's say that this weight has a mass of 10 kilograms. Cool. So if this is just hanging from the ceiling, a question we might want to ask is, what is the force due to tension? So I have a little Ft here. What is the force due to tension? If we drew a free body diagram, right, we know that weight goes down. So we have Fg here. And then we would know that tension is, well, it looks like it's pointing in the exact opposite direction, but we don't know with how much exactly. Well, what we can do is we can use Newton's second law. So, right, we have some forces in our y direction, but there's only one direction we're dealing with, so we'll just leave that little y subscript out. That's all I was talking about. And we ask ourselves, is this object accelerating in the y direction? It's not, right? It's just sitting there, it's just standing there. So our acceleration is actually just 0. So really what we just have is just this part right here, the sum of forces. So we're gonna break that down. We look at our free body diagram. We have one force, two forces. So we add them together. We probably want to, at this point, define a positive and negative direction. Usually, if something's not moving, you just use your normal cardinal direction. So like up is positive y, down is negative y, and that's fine. We can do that. So we'll say up is positive. So we'll have Ft plus Fg, and that equals 0. If we solve for Ft, we just have to get Fg to the other side. And so cool. So we know that our tension is equal to our weight, but we don't know what our weight is, but we can solve for it because remember, Fg equals mass times gravity, right? What is our mass? 10 kilograms. What is our gravity? Right? It's a constant. For us, it is a 10 meters per second squared. So really, when we plug that in, we have Ft equals mass times gravity. And then that becomes 10 kilograms times 10 meters per second squared. Right? What's 10 times 10? We get 100. Our unit, if we look at it, is kilogram meter per second squared. This kilogram meter per second squared, that's actually the definition of a Newton. So we really just have 100 newtons. Something I neglected to do because I was thinking too far ahead. When we move this Fg to the other side, we should have subtracted, so this should all be negative, right? So this is negative. But then something also to keep in mind is that this acceleration, gravity, is a vector, right? So it points downwards. So it wouldn't just be positive 10, it would be multiplied by a negative 10, right? So we have essentially, right, a negative, we have 10 kilograms times negative 10 meters per second squared, and then all of that multiplied by this little negative guy we have here. So that gives us a positive 100 newtons, which is consistent with our force of tension pointing up, right? So tension is not something where you have an equation. Usually it's something you look at the whole problem and then you solve for tension that way. But tension has to do with like that stretchy force. Finally, now we have our frictional forces, I should say. And there's two types. So the frictional force has to do with the surface of a material. So if right now, if you were to rub your hands together, I'm gonna do that really quick so you can hear the sound, right? You're gonna notice that they start getting hot, right? Because your hands have these little ridges on them, right? And when you rub them together, right, those ridges start vibrating. And so because there's a rough surface, they don't slide smoothly, right? If they were very, very, very smooth, right, they'd be able to slide very easily. So a frictional force is I'm going to call this a resistive force. Resistive force. And it depends, I'm going to start over here now, depends on the surfaces of materials. Oops. And they're actually going to even have a constant that dictates how rough a surface is. And so I'm going to show you the frictional force equations for static friction and dynamic friction, but we're not going to talk too much about them until actually your last lesson about forces in two dimensions. So really quick, force of friction, this is just capital F, little f, is equal to something called the coefficient of friction, denoted, this is Greek symbol mu. This is called the coefficient of friction. And I might have spelled coefficient wrong, but it's okay. And this multiplied by our normal force, right? So we know how to solve that. If we're on a flat surface, it's just going to be our weight. If we're on an inclined surface, then we have to find the angle and do some things that way. However, right, there are actually two types of frictional forces. There's a static friction, and there is a kinetic friction. I think I said dynamic earlier, I meant kinetic. Static is just kind of like what it sounds like, not static electricity, but non-moving objects experience static friction, while moving objects experience kinetic friction. And something that you may have felt before is that, let's say you're trying to move like a really heavy couch or a table or something like that. Like when you try to start getting it moved, it's actually pretty difficult, but actually after you start moving it, it gets a little bit easier. And so the way that these differ is simply like this. The force of static friction, denote with a little s here, is equal to mu s Fn. And sorry, this is actually deceiving a little bit. It's less than or equal to this amount. We'll talk about that a little bit more in a second. While the kinetic friction is equal to, and this one is equal to, mu k Fn. So kinetic friction is always just going to be a single value based upon your coefficient of friction and your normal force. So that's simple. This may look a little bit scary to you, but it's saying something very, very simple. Let's look at the example of, let's say there's a small box on the ground. This obviously exerts a force downwards because of weight. And then because it's not going through the ground, we know that there's normal force. Right now, let's say we moved this box, or we added some weight to this box. right? So now in a different situation, right? Could be the same box, but now maybe it has more stuff in it. So now the force of gravity, the weight, is a little bit bigger. Well, if that ground's not breaking or not deforming in any way, shape, or form, then the normal force is going to be just equally as big, right? And we can keep doing that until the weight of this box actually overcomes and breaks the structure of the ground. But if you notice, right, this ground can impart different normal forces based on the weight of this box. In the same way, right, when you have something that's moving, we can go back to this box example, right? Let's say the ground is a little bit rough, right? And even, if we went microscopically, right, this box would be kind of rough as well. We can have someone who's, maybe just gently leaning on it, right? And if this box doesn't move, right, this person's leaning on this box, so there's a force being applied to it. What's stopping that box from moving? It's the static friction, right? So it's applying a tiny bit of force. But now let's say this person starts to try and push it, right? He's applying bigger force now. If it still does not move, right, that means, well, we just increased our pushing force. And if it's still not moving, that means the static force increased to that much as well. But the thing is, the static force has a limit to how high it can go. Once we break that limit, right, the object begins then to accelerate. And then we switch down to a mu k instead of a mu s, right? It begins moving. There is a kinetic friction then, not a static friction. So those are kind of all of our different types of forces and the equations associated with some of them. Just to keep in mind which ones are, equation based, right? So this is for kinetic friction. This is for static friction. We can erase this little arrow now. For our tension, right? We look at our problem, we set it up, and that allows us to find the tension. Our normal force, it depends on the situation. If we're on a flat surface, normal force is equal to weight. Done. Easy. But if we're on an angled incline, then it can change. We can actually have different amounts, right? And then finally we have weight, which is simply equal to mass times gravity. So one more quick example, we also have something called the moon, right? There's little craters and things like that. The moon is much smaller, and its gravity is also going to be much, much less than the gravity on Earth. Right, so most of the problems that we do in physics, like 95%, are going to take place on Earth. So you don't really need to worry about that. You can always keep in mind that gravity is 10 meters per second squared. But on the occasion that I ask you about a different planet, just keep that in mind that then that gravity may not be the same thing that you are used to. So that's all I have to say about these different types of forces. You're going to be using them a lot more. But know that since they are all forces, they are all measured in newtons, right? They are all forces that change the motion, or they attempt to change the motion of something, or in some cases resist it, right? Because a frictional force kind of resists changes in motion. But in a way, they all have like the same feeling. And I shouldn't be using this word feeling, but I think to some degree, right? We know that we learned initially that a force is a push or pull, and all of these different types of forces are things that are just pushing or pulling on the different objects that we have. And so, yeah, that's all. You should definitely look up more information about different types of forces. There's even more like compression and like air resistance and things like that. But these are the main ones that we're going to focus on. One last thing to keep in mind is just that there may be times where I give you like a random sounding force, like maybe like air resistance. You can always just treat that like a general force, just something that you can calculate by looking and analyzing the problem, very similar to how we found this tension force. So that's all I have for you today. Thanks so much. Have a good rest of your day.